Hello, dear explorers. We will study quantum mechanics. The study of quantum mechanics starts very before the origin of the subject. Humans were curious about the patterns of universe, like phases of moon, the constellations, and the one thing that was most visible was light. Christian Huygens proposed that light is a wave, and there is an invisible medium in the universe called ether, and the light that is a wave travels through that medium. So Michelson and Morley experiment proved that there was no such ether present there. Meanwhile, James Clerk Maxwell was working on electric and magnetic fields and found out that actually electric field and magnetic field are related. An oscillating electric field generates oscillating magnetic field, and oscillating magnetic field generates an oscillating electric field. And he told of electromagnetic waves like X-rays, gamma rays, and he find out the velocity of that electromagnetic waves is equal to 1 by under root of mu naught and epsilon naught. So this is the velocity of an electromagnetic wave in vacuum, where mu naught is magnetic permeability and epsilon naught is electrical permeability. So what he found that this speed of electromagnetic wave was exactly equal to speed of light in vacuum. So it was then well established and proved that light is an electromagnetic wave. It was well established and proved that light is an electromagnetic wave. And as Clark explained, that electromagnetic wave does not require any medium to travel because an EM wave consists of oscillating electric and magnetic fields and they generate each other and hence the wave propagate. So light is an electromagnetic wave that does not require any medium to travel. So at this point, that light is an EM wave. It was well established, well proved that light is a wave. So many experiments were explained on the basis like laws of reflection, laws of refraction, interference, diffraction pattern. All these were explained on the basis of wave theory of light. Now, when did the actual problem came? There were light experiments which could not be explained by wave theory, and they were first was photoelectric effect. First was photoelectric effect. Second was Compton effect, and third was ultraviolet catastrophe. So these three light experiments were not being able to prove by light theory. So Mr. Einstein here proposed that light, along with being a wave, is also a particle, and he named that light particle to be photon. He named that light particle as photon. He proposed that light come in packets, in particles, like electron is a particle, proton is a particle. So light also comes to us in the form of a particle in a packet called photon. So with this, so this is called particle theory of light. Light is a particle named photon, and all these three experiments were explained by the particle theory of light and the term wave particle duality was established, that light is a wave as well as a particle. Light is a wave as well as a particle. Light is both. So uh, everyone knows the story up to this. So now comes the main confusion, and I hope everybody would be confused in that. So my question is that if light at the same time is a wave and at the same time it is a particle, then do we actually mean by it? If light is a wave and also light is a particle, then what do we actually mean by it? 99.9% will answer a certain thing. That is, when we say that light is a particle and wave at the same time, then they will give a certain specific answer, that we have a photon and it will travel like this. We have a photon here and it will travel like a wave. So suppose this is a photon, it will travel like this. Everyone will have the same answer, approximately everyone, that a photon will travel like this, just as a sine wave. So you would try to answer that this is the meaning of wave particle duality, that the photon travels as a wave. And everyone is confused here, and if your answer is this, then you are wrong. So what do we mean by that light is a particle at the same time and light is also wave at the same time? Before answering this question, let's go a little ahead. After that, after this light step having a duality nature, what came the next? Next came de Broglie hypothesis. Hypothesis means a proposal. So he proposed in his PhD synopsis that if light, which was a wave, has a particle nature, then a particle must also have a wave nature. Like light is an EM wave and it has a particle nature, photon. So a particle such as electron or proton must also have a wave nature. And he said that particles are also waves. He proposed that. So by Davidson and Germer experiment was performed on electrons, and that electrons actually showed interface diffraction pattern, which is a property of waves. So it was proved by Davidson and Germer that particles also have a wave nature. So this particular point is the origin of quantum mechanics. That a particle is a wave also and a wave is a particle also. Are you clear till here? Now we are going to answer your questions. That might be confusing all along your journey, all along your quest, all along your voyage. So my question is, just imagine, when I say that an electron is a wave, then what do I actually mean? It is a wave of what? When I say that an electron is a wave, then what do I mean by that? For example, let us take a water wave. Like, like water, let us take the example of a water wave. So in water waves, water molecules vibrate, and in sound wave, air molecules vibrate. Okay, so does it mean that in an electron wave or in a particle wave, suppose there is an electron and I say that there is a wave associated with it, does that mean it vibrates just as a water molecule vibrates, oscillates? Does it mean that does de Broglie meant that an electron vibrates about its position and that he named as a wave associated with that electron? No, absolutely no. To try any other thing, okay. So an electron is a wave of what? So the answer is an electron is a wave of probability. So electron is a wave of probability. Now, by this statement, you might be remembering this symbol, which is the core of quantum mechanics, and we name this symbol as psi. Our concept is to explain this symbol. What do we mean by psi? So, an electron is a wave of probability. Now, what do we actually mean by that? So, for example, you might be familiar with the shape of the s orbital. So suppose there is an electron having energy, and that electron having energy such that that electron occupies the 1s orbital, suppose. So this is the shape of the 1s orbital. Now please be slow and try to listen this carefully. By wave of probability, we mean that a wave of probability, we mean that at the same instant of time, at the same instant of time, this electron is here also, here also, here also, here also, here also. Okay, so in going in detail, let me first explain you what is the difference between a particle and a wave. So consider a particle. I hope this was the s orbital. So let me tell you the basic difference between a particle and a wave. So a particle is localized. A particle is localized. That at a certain instant of time, it is just at one place. At a certain instant of time, a particle is just at one place. There is a wave. Wave is not localized, or we can say it is spread. It is spread over space. Like, consider a water wave. At the same instant of time, this wave is here also, this wave is here also, this wave is here also, this wave is here also. Whereas the particle is only at one point at a certain instant. Whereas a wave, at the same instant, it is at many points. So a wave is non-localized and a particle is a localized. So now we come here. We said that electron is a wave. Electron is a wave and it is a wave of probability. What do we mean by that here? Suppose as an electron in 1s orbital. So this is the shape of 1s orbital. It means that it is a wave, electron is a wave that at the same instant of time, this electron is here also, here also, here also, everywhere, every possible space. It is spread just like a wave. just at the same instant of time, the wave was here also, here also, here also. Similarly, an electron, which is a wave, at the same instant of time, it is here also, here also, here also, here also. Let me make it clear that I does not mean that after one that at 1 second that at time is equal to 9 a.m. it is here and time is equal to 9 1 it is here. I does not mean by that it is changing its position with time. It is not moving here and there. I mean that at the same instant of time it is everywhere. One electron. These are not many electrons, this is only one electron, and at the same instant of time it is spread everywhere, just like a wave. So electron is a wave. So this is what we call the electron is a wave of a probability. Now when it takes the case of a particle, when it becomes a particle, when we observe it, these are all the possible space where an electron can be found. So at any instant of time, it is everywhere in this region. But when we observe it, when we observe it, when we observe it, it takes one possible position out of all. It was everywhere when we were not observing. But when we observed it, it took only one possible position. Means it became a particle. It means when we were not observing the electron, it was a wave, it was spread over space. But when we observed it, it took only one position. That means it became a particle. This is what we mean by electron is a wave and a particle. It is a wave when we do not observe it and it becomes a particle. It takes a specific position when we observe it. And this is called Copenhagen interpretation. There were three interpretations of quantum mechanics, and this was one of the three. But the 2022 Nobel Prize confirmed that this interpretation of quantum mechanics is correct. Now, does that astonish you? Listen carefully again. An electron is a wave. That means at the particularly same instant of time, it is everywhere, spread over the space. But when we observe it, it takes only a single position, it becomes a particle. Okay, these are not many electrons. This is just only the one electron and it is spread everywhere in this space when we do not observe it. But when we make a measurement and we observe, it becomes a particle and takes only a one position. So this is the breakthrough of quantum mechanics. This is the core of quantum mechanics. I want you to replay my last 10 minutes so that you can actually know what is the origin of quantum mechanics. What are the astonishing questions that quantum mechanics put ahead us? See, electron, which we thought as a particle, is not a particle, it is a wave. By wave means at the same instant of time, one electron is spread everywhere. But when we measure it, when we observe it, it takes a specific position. Okay? So we see that light is a wave and light is a particle when we observe it. Then what an electron actually is a wave packet. Electron actually is a wave packet. What is a wave packet? A wave packet is a superposition of many waves that is confined in a region. So this is a wave packet and this is an electron. This is a wave packet and actually this is an electron. This is the reason where there is a probability that electron will be found when we will measure it. So this reason, particular reason where probability is maximum of finding the electron, I have drawn diagrammatically, and the same thing now I have drawn mathematically or graphically. This is the reason where electron is supposed to be found, and this is the reason where electron is supposed to be found. This is diagrammatically, this is graphically, mathematically. So this we called a wave packet, and actually this is an electron. An electron is a wave packet. Means at a particular instant of time, it's everywhere in this region, but when we will observe it, when we will measure it, it will take only the one specific position of this region. So an electron is a wave packet, and a wave packet means superposition of many waves. Okay. So shall I go next? And I will explain. I will try to explain now Heisenberg's uncertainty principle, and uh, let me rub this. So, according to de Broglie, lambda is equal to h by p. Lambda is equal to h by p. This is the de Broglie wavelength. Now, this equation looks very simple. Looks like it is a general equation, but see a little thing. Lambda is a property that a wave has, and p, momentum, is a property that a mass has. So this equation means that a mass has a wavelength. This equation means that a mass has a wavelength. So could you see how astonishing this equation is? A mass is having a wavelength associated with it. Okay, so Heisenberg uncertainty principle. So suppose I want to, it says that we cannot accurately measure the position and at the same time accurately measure the momentum of a electron or a proton or anything on a detailed scale. Suppose we want to measure the position accurately. Here is a wave packet and we want to measure its position accurately. So we will need that lambda should be minimum. We would need that lambda should be minimum so that position is accurately measured. For example, we have a wave that has this lambda and we have another wave that has a small lambda, which will be whose position will be accurately measured. This wave's position will be accurately measured. But if we have a less lambda, we will have a greater frequency. And if we will have a greater frequency, we will have a greater momentum. So, if we will try to measure the position effectively, we will get some error in the momentum because for accurately measuring the position, we need a low wavelength, but that certainly gives high momentum, which leads to an error, because measuring a position means we want this lambda very near to zero, and when we make this lambda very near to zero, the energy, the momentum comes very near to infinity. So this is the core of Heisenberg uncertainty principle, that we cannot measure an electron position and momentum effectively accurately at the same time. We will always get an error, and this is Heisenberg uncertainty principle. So, okay, I introduced that an electron is a wave packet, means a wave confined in a space. By electron is a wave packet means an electron is confined in a space. But see, what is a wave? A wave is a disturbance. A water wave is a disturbance in water. A sound wave is a disturbance in air. Then an electron, for suppose, is a disturbance in what? Electron is a wave, and it means that it is a disturbance. So it is a disturbance in actually what? So here comes quantum field theory, and it says that vacuum, that in the universe there are 7 fields, and an electron is a disturbance in the electromagnetic field. Electron is a disturbance in the electromagnetic field, because when we say vacuum, it means no air, specifically no medium, no air. But a vacuum does not mean zero energy. Vacuum has fields in it, and the Casimir effect is the actual proof for that. An electron does not mean, a vacuum does not mean zero energy. So an electron is a disturbance in electromagnetic field. Do you remember the God particle that was discovered in 2012? It was the proof that Higgs field actually exists, which proved us further that quantum field theory is correct. So let me sum up this everything. So this is an electron, which is a wave and a particle at the same time, and by that we mean that it is a wave packet. By wave packet we mean that it is a wave confined over a certain region. At the certain point of time, it is everywhere possibly in this region. But when we measure this, when we observe this, it takes only one specific position out of all these possible positions. So that's why we say an electron is a wave of probability. And we represent this wave packet by psi, which we call wave function. We represent this wave packet mathematically by a psi, which we call wave function. So I want you to listen my video, certainly in repeat mode, so that you can acknowledge that what quantum mechanics actually is. Thank you.